Good morning and welcome to this postgraduate video course on advanced hydrology. We have been into chapter 11, we started it yesterday, which is on stochastic hydrology or hydrologic statistics. We defined a certain basic concepts about probability, the sample space, the population and so on. All right. Then we looked at some basic laws of probability. All right. When we say that when we have more than one event, then we need to look at what are the interrelationships between these different probabilities of these different events. Okay. Then we looked at the concept of what is called the frequency histogram, frequency analysis, in which we try to find out the relationship between the magnitude and the frequency of occurrence of a particular event. And that event, as we said, can be defined in any manner as we want, because it will be based upon what is the objective of that particular analysis. Then we looked at the concept of relative frequency function and the cumulative frequency function. We said that these things are for some sample, all right, or discrete data points. The corresponding functions for the population we defined as the PDF or the probability density function, or the CDF, which is the cumulative distribution function. All right. Towards the end, we had written down a relationship between the PDF and CDF. All right, and I had said that I would like to emphasize, in fact, that the understanding of what does a PDF represent and what a CDF represents, it is extremely important. All right. So, what we are going to do today is we will get started from where we left off and look at the relationship between a PDF and a CDF. So, if we come here, then we will this is where we had actually left off. We had said that small f is nothing but the PDF, which is what? Which is the slope of your CDF. All right. And then we had also said that the f of x, right, can be defined as the integral from the lower limit or the range up to some point x of your PDF. All right. And what does this or rather I should say fu du, okay, because x is a number there. So, I can say fu du or ft dt or something like that. All right. What does this represent? Well, this is nothing but p or probability of a random variable x having a magnitude less than equal to small x. Okay. We will visit these concepts in a little bit more details today. Okay. So, let us look at the discrete hydrologic variables. How will these functions look like or be defined for discrete hydrologic random variable? As we said, for discrete data points, what are the functions? These are called relative frequency function and the cumulative frequency function. That is what we had defined. Okay. So, if I just plot them here, okay. So, this is your variable x and this is your f of your xi or the frequency of occurrence of that particular event xi. This is your x1, x2, x3, so on up to xi and all the way to xn. All right. So, there are n number of data points and each one of them has certain probability of occurrence. Okay. For a uniform distribution, they all may be same, but if the data follow certain other distribution, this distribution will be according to that particular PDF. Okay. Now, what is this? This we are saying is your relative frequency function. Okay. And if you take the mass curve of this for a discrete variable, it would look something like this. All right, where you have this as x1, x2, x3, xi all the way to xn. Okay. What will be the maximum value. Okay. It has to be equal to 1. The cumulative of all the probabilities from a relative frequency function, they should sum to equal to 1, or the mass probability of all the events has to be equal to 1. Okay. All right, and just to complete it, we are defining here capital F of your x I here. Okay. And the relationship is that your f of x for your sample is nothing but the summation of your f of it is, because we are defining this for a sample of your x I, such that your x I is less than or equal to some value x. All right. And what is f of x I? This would be equal to the difference of your cumulative function at the boundaries, or x I minus 1. Okay. So, this is an important relationship, both of them. All right. So, this is about the discrete hydrologic random variables. All right. We have the similar thing which is called the PDF and CDF, and we are going to look at the interrelationships and what kind of probability each and every expression represents. So, if you come here for the continuous hydrologic variables, okay, what is it? This is a PDF, as the shape suggests, that is your small f x. So, this is your probability density function for your hydrologic variable. If we take the value x 1 and x 2, all right, then this area under the curve represents certain kind of probability. Okay. Area under the curve, which is PDF, will represent a very specific probability, and we will look at it in a minute. So, let me first draw the corresponding CDF, which is represented by capital F. Okay. It may look like this, and as I said, the maximum value is always 1. Okay. So, here if you take same magnitude x 1 and x 2, the corresponding values of your CDF are, let us say, f at x 2 and f at x 1. So, what is this? This is your CDF function, or this curve is representing your CDF, which is f of x. Okay. So, if you take any 2 points, that is what it will represent, and we have seen, or we know that what is f of x? It represents a certain kind of probability, as I said. All right. What does this represent? Well, it is the probability of your random variable x having a value less than or equal to x. All right. So, from that point of view, you can say your f at x 1 is nothing but the probability of x having value less than or equal to x 1, and f at x 2 will be the probability of your random variable having a value less than or equal to x 2. Okay. All right. So, if I write it here, you have f of x is equal to probability of your x being less than or equal to x, which in terms of the PDF will be what? It is representing nothing but area under which curve? The PDF from minus infinity to x. Okay. So, what we are saying is that the f of x, all right. So, you have a CDF curve on which any point x 1 you take or x you take, its ordinate is capital F of x. All right. What is this representing? This capital F of x is representing the area under the PDF, all right, all the way from minus infinity or 0, whatever the range, minimum range is, all the way up to that value x, all right. So, if you come here on this curve, what is your this f of x? This is nothing but the area under the PDF all the way from minus infinity to x. So, that will be actually all of this area. So, that is your capital F of x, all right. Now, moving further, let us look at certain properties of these PDFs and CDFs. Okay. These probability distribution functions, all of them will have to satisfy certain properties to be defined or to be used as the PDFs and CDFs. Okay. So, let us look at them. First one is that all of them have to be non-negative or greater than 0 for all values of x. So, the value of your CDF has to be equal to or greater than 0. Another very important property is this, minus infinity to infinity of your f of x dx will be equal to what? Can somebody tell me this? That is the area under the whole curve of your PDF, which is nothing but the cumulative value of your all the probabilities. That has to be equal to what? 1. Okay. As per your definition of your CDF, that has to be equal to 1. So, this is an important relationship which is very helpful in finding out the equation of the PDF many times. Let us move further. What will be the area under the PDF between x 1 and x 2? What would this be? Can anybody think about it? If I go back, this is my PDF, this guy here. This is x 1 and x 2. So, if I take the area under the curve, which is the shaded area, all right, this one, this represents the area under the curve from x 1 to x 2 of what? F of x dx, right. That is what I have written on the next page, all right. And what is this? This is nothing but the probability of occurrence of your random variable such that it occurs in this range x 1 and x 2. Okay. So, you see that this PDF is extremely important because it not only gives us the information about the frequency of occurrence of a particular value. If we take the area under the curve of the PDF, this will give you the probability of occurrence of the random variable between that range, okay, the minimum and the maximum, which is very useful in the drought analysis or the flood analysis or any kind of analysis of any physical system which is stochastic or uncertain in nature. Okay. Continuing further, how can we find this probability? If we know the PDF, we can take the area under the PDF between x 1 and x 2. However, let us say we do not have the equation of PDF, but we have the equation of the CDF or the cumulative distribution function, right. Can you find this probability of a random variable falling between a range x 1 and x 2 given the CDF? Yes, and that is going to be what? Simply the ordinate of your CDF at x 2 minus ordinate of your CDF at x 1. Okay. What is this equal to? This we have already defined or said. What is this? These things are given here, right. The ordinate of a cumulative distribution function at any point gives you what probability? These probabilities, all right. So, if you go back and say what is this equal to? This is nothing but your probability of your random variable being less than or equal to x 2, this probability minus x less than equal to x 1. Okay. Do you see that? If you look at the curve, this is your PDF, all right, and that is your CDF. So, what we are saying is that this ordinate minus this ordinate. So, this thing here, okay. This thing is representing what? This thing, which is equal to this whole thing, all right, this probability, this one. Okay. So, we see that if we know the equation of a probability density function or the cumulative distribution function, there are lots of these interrelationships which we need to understand, and we can deduce one type of probability from the other and so on. So, these kind of understanding is extremely important when you are analyzing your hydrologic variables which are uncertain in nature, all right. So, this was a very basic background about the probability and the related concepts, all right. We have been talking about PDFs, all right, which is a probability density function. So, what we are going to do next is we are going to look at a extremely popular and important probability density function. Okay. If you have studied statistics anywhere, you would have studied this PDF or the probability distribution. This is called the normal distribution. You will find it in any book on statistics at any level. All right. So, let us look at the normal PDF. First, we will look at its equation, and then we will look at an approximation, all right, because in computers we cannot have the tables. Okay. So, let us look at what we call as the normal PDF. I am sure you may have seen the equation of the or the shape of the normal PDF, which actually would look like this, all right, where this is your x and this is your f of x, all right. It is symmetrical in shape, okay, and it goes from minus infinity to infinity. The range of the x can be minus infinity to plus infinity, all right. The equation of the PDF is given as follows. E to the power or exponential of your negative over twice of sigma squared. I am sure you may have seen this equation earlier. So, this is the famous PDF for the normal distribution, okay, where let us define all these parameters. Mu is the mean and sigma is what is called the standard deviation. Both of these are called the parameters of the normal distribution or your normal PDF. Okay. Now, this is a complicated equation where the range of the variable can go from minus infinity to infinity. Those of you who have seen the normal distribution or normal PDF know that we redefine this normal distribution in a different dimension or in different reduced variate or different type of variable, which is called z or the normal reduced variable. Okay. So, normally what is done is it is simplified in the form of what is called standard normal variable using z. Okay. So, we normally simplify this and we define this using standard normal variable. How is that defined? Z is nothing but your actual variable minus the mean divided by the standard deviation. Okay. Once we use this transformation, the equation for your PDF will become equal to this. e to the power minus of your z squared by 2, and the z will also go from minus infinity to plus infinity. Okay. And the capital F, I am sorry, I am writing x here, it should be z. Okay. Similarly, f of z is going to be equal to the cumulative of that curve, that is from minus infinity to what variable now? We have reduced everything to z. All right. So, it is going to be 1 upon under root 2 pi of the same thing, e minus, I am going to use u square by 2 du instead of z, because z is the limit here. Okay. This is your equations for standard normal distribution. Okay. Where what is this? This is your CDF, or the cumulative probability of your random variable being less than equal to z as per the normal distribution. This is available in standard tables. Okay. What is available in standard tables? Values of z versus f of z. Okay. So, z is the standard normal variable and f of z is the cumulative distribution function. Okay. So, this standard normal distribution, the CDF is available as a function of z, all right, and this is available in the standard tables which you will find at the end of any book. Okay. So, it is very easy to use. I am sure you have seen the examples, and we will probably look at an example little later. However, when we are analyzing a complicated project in which we need to refer or we need to determine some kind of probability which follows a normal distribution, then we will have to refer to these tables very frequently, all right. And when we have a complicated program or a computer program in which these probabilities are needed, then it becomes difficult to either we have to just input all these values and then read the particular values, all right. We will not be able to do much as far as the accuracy is concerned, and it is more laborious also. So, what some people have done is they have tried to approximate the cumulative distribution function values given the value of z for a particular normal distribution, all right. So, what we are going to do next is we will look at the approximation of this capital F of z or the normal CDF, all right. So, let us look at that. Excuse me. So, next thing we will look at is what is called the approximation of your F of z. Okay. Many people have tried, and this is quite accurate, which is given by this equation. This F of z is some variable b for all the values of your z less than 0 or which are negative. Okay. As you see the value of z from here, all right, you are subtracting the mean. So, z will be having positive and negative both the values, all right. So, for the negative values of z, f of z is given as b, and it is given as 1 minus b for all values of z which are greater than or equal to 0. Okay. Now, what is this b? This b is defined as, it is a long expression. So, I am going to write it, you just bear with me, okay, with lots of numbers. Half of 1 plus 0.196854 the modulus of z or the absolute value of z plus 0.115194 of your z square plus 0.000 of your 344 modulus of z cubed plus 0.0195 527 z of your 4, this whole raised to the power minus 4. Okay. So, you see that this is some kind of expansion, Taylor series expansion, or some kind of expansion of a function in which the order of expansion is up to order 4, okay, which is considered quite accurate. All right. And this will give you an error, this function. It has been shown and tried using many experiments as error less than 0.3025, which is good enough. So, you see that we can use this expression, all right, this approximation of your f of z, this whole thing, in a computer program very easily, all right, which will give you quite accurate value of your f of z given z, which is useful in a computer program while you are analyzing certain water resources management problem. Okay. The next thing which we are going to look at is a concept which is important to understand, because we have many kinds of these PDFs, all right, and each PDF there are certain parameters which will characterize that particular probability density function. All right. So, what we will do next is we will look at certain parameters of these PDFs which we need to calculate, or we need to understand in order to be able to fit those PDFs to the data and then understand what they are actually representing. All right. So, the next thing we will do is what is called the statistical parameters. Okay, of PDFs, of course. How do we characterize these PDFs? We do that by using many statistical parameters, okay, and we will look at 2 or 3 of these parameters. Okay. Can anybody think about any statistical parameter which we use to characterize a PDF? Well, we use the expected value is the first one, or the mean of the PDF. So, we will go one by one. The first one is what is called the expected value. All right, and this is denoted as EX, expected value. What does this give us is what is called the measure of central tendency. All right. What is a measure of central tendency? Well, this gives you an idea about where on an average most of the data are expected to lie. They will lie close to the expected value, which is also equal to the mean or the average value, right. So, the highest frequency will occur around the mean. All right. So, this is one of the measure of central tendency. There are other measures of central tendency we will not actually look at, like mode and median and so on. All right. So, expected value is nothing but the mean, right. So, how is it defined? This is mathematically defined like this. Expected value of x is denoted as mu, all right, is equal to the integral over the whole range minus infinity to infinity of your what? X times of your f of x dx. Okay. So, what we are doing here is, if you look into this integral, we have the PDF f of x, all right. So, what we are doing is we are taking different values of x, we are multiplying that by its frequency, all right, and then we are just taking the moment about the origin, all right, when we will rotate this curve. So, it will be nothing but the area under that curve when we are rotating it, all right. So, let me define it. This mu is nothing but the mean of the variable, f of x is of course your PDF, and x is the value of your RV capital X. Okay. This E of x is also known as aka as the first moment about the origin. Okay. So, what is the expected value in statistical terminology? It is also called the first moment about the origin. First moment of what? First moment of your PDF. All right. So, you take the PDF, multiply the respective values of x, all right, by this PDF, and then you take that function and integrate it. That will give you the expected value. Okay. Now, this equation which we have written is for the population. All right. How about a sample? The sample estimate of your first moment about the origin or the mean is nothing but what we call as the sample average x bar. We all know how x bar or the average is defined. It is nothing but 1 by n multiplied by the summation of all the values, isn't it? Okay. Now, do you see the similarity between these two equations? That is this one and this one. They are same. Okay. One is for the population, other is for the sample. Okay. One has x multiplied by f of x. All right. What is x? X is the value of your variable or the sample value or the observed value. Okay. So, if you come here, this x, all right, is your this xi. All right. What is the frequency of occurrence or the probability corresponding to that value of x? In this particular case, you can write this expression as what? Summation of 1 by n if you take inside times xi and I going from 1 to n. All right. So, what is this then? This is your nothing but f of x, which is the frequency of occurrence. Okay. So, if you have a sample of observations, let us say 20, 30, 100 observations, each value occurs once. What is its frequency of occurrence or probability or some kind of fraction? It is nothing but its probability is 1 by n, its frequency of occurrence is 1 out of n. All right. So, this 1 by n represents nothing but the PDF or the f of x. All right. So, that is how you see that these two expressions are nothing but the same. So, this is about the expected value or the central tendency where the mean of the whole PDF is. Okay. The second characteristic is what is called the variance, which is sigma squared, which is the measure of what? As the name suggests, measure of variability in the data. And it is also called measure of the spread in the data, how the data are spread around the mean. Okay. And this is also known as the second moment. Known as what? The second moment about not the origin, but the mean. Okay. The first moment, which is the expected value or the mean, is always defined about the origin. All right. And the higher order or the other characteristics or these other moments, that is second moment, third moment, fourth moments, these are always defined with respect to the mean itself, because once we have calculated the mean, we can find out the deviations with respect to mean and we can analyze those. Okay. So, how is this second moment about the mean defined? It is nothing but the expected value of x minus mu whole square. All right. So, what is it? Square means it is the second moment, with respect to mean means you are subtracting the mean from your x values. Okay. And this is nothing but, as we said, sigma square, or which is the variance. So, if you take this, how will it be defined? It will be the integral between minus infinity to infinity of what? You have the PDF which is f of x, you will multiply that by what? X minus mu of your square. So, you will take each data point, subtract the mean from it, square it, multiply by the PDF and then keep on doing it for all the data points. All right, you integrate your PDF like this, or the modified function like this. Okay. So, this is called your variance, equal to your, okay. This type of moment will give you an idea about the how the PDF is spread around the mean. Is it very large or is it very small? All right, I will draw the figure and we will come to that later. Okay, what about the sample? The sample estimate of variance, okay, is denoted actually in terms of what? In terms of this variance denoted as S, and normally we take the standard deviation. What is standard deviation? It is nothing but square root of your variance, which is this. So, it is nothing but your S. Okay. All right. So, if you look here, this is your random variable x or hydrologic variable x, this is your PDF. Okay. So, you have one PDF like this, you may have another PDF like this. Okay. Their means are nearly same. All right. Which one has a larger variance than the other? One obviously with which is very narrow around the mean value or the average value has a smaller spread around the mean. Okay. The other one which has a flat peak or which is more spread has the higher variance. So, if you see here, this one is what? Large variance, and this one shows small variance or sigma, you can say. Okay. So, this way you see that we can calculate the if we have the data, all right, about a particular physical phenomena which is uncertain in nature, we can calculate the mean, we can calculate the standard deviation, and that will give us an idea about the where is the central tendency of that data, what is the average, all right, and how spread the data is about the mean. Okay. For example, in a school you may have 2-3 different sections in a class. Okay. So, in that class after the examinations you can calculate the statistics or the statistical parameters of each class. So, you can compare the two classes. For example, one class may have an average of 80%, another class may have an average of 60%. So, you will be able to say that on an average this class is better than this particular class. All right. Similarly, you may have two classes in which let us say the average is same. You have two sections in which average is 70%, both of them. But if you look at the range, the data in one class, most of the students may be close to 70. Let us say the variation is from 60 to 80. There may be other different class in which the variation may be let us say from 20 to 100. All right. So, there will be more variation. There are students of varied background. So, this kind of information on variance and means give us a lot of information about the characteristics of the data or the PDF which they follow. Okay. So, we will move on and look at a third statistic or statistical parameter which is called a skewness. As the name suggests, it is what? It is a measure of symmetry in the data, or symmetry or asymmetry of a data set or a PDF. It is defined as the third moment about the mean. Okay. We are going up to higher moments here. It is defined as the third moment about the mean. Okay. All right. So, how is it done? As we have seen, it will be nothing but the expected value of what? X minus mu to the power what? Third moment we are taking cube. This will be equal to what? Minus infinity to infinity of what? X minus mu to the power 3 of course, and then the PDF. So, this will give you the third moment about the mean, and this will measure the skewness in the data. What is the skewness? Most of the PDFs or the for example, the normal PDF, if you have seen, it is very nice and symmetrical. All right. At the center, if you look at the two sides, the two sides are the mirror image of each other. It is exactly similar. All right. So, if you fold a PDF or normal PDF, it will match. All right, like this. However, all the PDFs are not like this. All right. There is asymmetry. Okay. One may rise very quickly, the falling limb may be slightly different or may be too long. Okay. So, this third moment about the mean, which is called the skewness, it is a measure of asymmetry or symmetry in the data set. Now, this particular expression has what will be the dimension of this? For example, let us say your random variable is rainfall. All right. So, what is the units of rainfall? Well, let us say it is centimeters or inches or whatever. So, what will be the units, let us say, of your expected value of x minus mu to the power 3? If you look at this equation, this is dimensionless of course. All right. What is the unit of x? Centimeter. What is the unit of mu? It is also centimeter. All right. So, it will be what? Centimeter cube. All right. Or same as the cube of units of your random variable. Okay. So, if it is representing flow, which is meter cube per second, what will be the units of this third moment? It is meter cube per second raised to the power 3. Okay. So, then what is done is normally the coefficient of skewness is defined, which is dimensionless. All right. For mean and for variance we do not do that. Let me go back actually and emphasize what will be the units or dimension of this, the mu or the first moment about the origin. All right. I can say same dimension as your random variable. Okay. So, the units of your expected value of x is same as the units of your random variable. If it is rainfall, if it is centimeter, expected value also will have the same unit as centimeter. If it is peak flow, annual peak flows, meter cube per second or feet cube per second, the mean also will have the same dimension or same units. What about the variance? This one, this will have the square of the original units. Okay. So, if you have rainfall, the units of your variance will be centimeter square. All right, but we keep it like that, we do not modify that. However, it is a usual practice to represent your third moment about the mean or the skewness in terms of what is called a coefficient of skewness, which is dimensionless. Okay. Otherwise, the values will be too large and you have to write the dimension all the time. Okay. How can you do that? Let us say this is the coefficient of skewness, it is defined as gamma. How can you make this expected value x minus mu to the power 3, I divide by a quantity which has units of same as the numerator. All right. So, what I do is this. Okay. So, this is your nothing but coefficient of skewness, which is expected value of x minus mu cube or third moment about the mean divided by the standard deviation to the power 3. Okay. All right. What about the sample estimate of your coefficient of skewness? that is a theoretical value. This is denoted as CS or coefficient of skew and defined as this particular expression. It should be easy to derive it, but we will not go into the details. Xi minus x bar raised to the power 3 divided by n minus 1 and n minus 2 and s to the power 3. Okay. So, this is the expression of your coefficient of skewness. So, if you were to be asked to calculate the coefficient of skewness and you are given, let us say 100 data points, how can you do that? Just use this equation, all right. Subtract the mean, you take the cube of that, all right, and then use this expression. You can do that easily, all right. So, this will give you an idea about how the data is skewed. Okay. What will be the value of your coefficient of skewness? Will it be positive? Will it be negative? Well, as you can see, it is appearing as xi minus x bar to the power 3, all right. So, depending upon the cumulative values of these deviations, all right, whether they are positive or negative, it will, depending upon that, you will have the coefficient of skewness either positive or negative. Okay. So, you see that this summation I is running for the whole data point, number of data points. Okay. So, it can be positive, it can be negative, or it can be 0 also, all right. So, for the normal PDF, which is perfectly symmetrical, all right, which is perfectly symmetrical, the coefficient of skewness is what? It is 0. Okay. And then if you look at other PDFs, I will just give you a diagram where you have this as your hydrologic variable x, and this one is your f of x or the PDF. Then you may have a PDF like this. So, you see that this one is skewed to the left, all right. More of the data points, all right, are concentrated towards this peak, all right, and to the left of your in the middle points. So, this is called a positive skew. Okay. The other one may have a shape like this. Okay. And this is what is called a negative skew. So, this CS, the coefficient will come out as less than 0, and for this one the CS will come out greater than 0. Okay. And there is another expression, this is one we have seen. Certain books you will find the CS as given by this n square times summation of xi cube, I going from 1 to n, of course, that is 1 minus 3n of your summation xi, I going from 1 to n, times xi square, again I going from 1 to n, plus twice of summation of x cubes all right. All of this divided by n times n minus 1 times n minus 2 times, of course, s to the power 3. Okay. So, this is another way of defining your coefficient of skewness, which gives us an idea about the asymmetry of the particular probability density function. Okay. So, this way you see we have seen 3 different types of statistical parameters, which give us some idea about the characteristic of the PDF. All right. So, just to summarize, if you are on a plain piece of paper, if you have some PDF like this, the mean will tell you what? Mean gives you an idea about where most of the variables or most of the observations are going to lie, all right, around. Okay. You see that. So, this is the most expected value, all right, around which you will have other observations. Okay. So, most of the observations will be lying around the mean. So, this gives you a measure of central tendency where on this x axis your mean is going to be, or most of the values are going to be. Second one we have seen is it will give you the information about what? About the spread, how the data are spread around a particular value. All right. So, this is your mean. This will give you the area about the variance or the spread. Okay. And the third one we have said is how symmetrical or asymmetrical a PDF is. So, this gives you an idea about the symmetry. All right. And actually there is one more moment which we have not looked, which is normally used very rarely. In fact, sometimes you know, whenever we are fitting probability distributions, we can get away with using these 3 distributions, or rather 3 statistical properties, or the 3 moments. All right. First moment about the origin, second moment about the mean, and the third moment about the mean. All right. We also have what is called a fourth moment about the mean. Okay. It gives you an idea about the how sharp the peak of the PDF is. This is called the measure of peakedness. Okay. So, if you define it theoretically, it is called a measure of peakedness of a PDF. Okay. So, how is this defined? Let me do that quickly. It will be raised to the power 4 because this is the fourth moment, and it will be the same thing minus infinity to infinity of your x minus mu to the power 4 of your f x dx, right. And then if you look at that graphically, you may have a PDF which is quite sharp like this. You may have a PDF which looks like this. All right. So, this is very sharp peak, and this one is less peaked. Okay. So, it is a measure of the peakedness of your peak value, all right, or how the observations are centered around that particular value or the maximum value. Okay. Now, corresponding to this measure of peakedness, we define a coefficient of peakedness, but I think we will not go into those details. Higher the coefficient, higher will be the peakedness of a particular PDF. So, you see that today we have seen all these different types of moments of or the PDF. What is the relationship between the PDF and CDF? All right. So, I think I would like to stop at this point of time, and in the next class what we will do is we will look at 2 important methods of fitting any PDF to a given data set. Okay. So, we have seen the background about the probability, statistics, basic concepts, and what is a PDF, CDF, and how they represent, what are the different characteristics. All right. With all that background, we will look at how we can fit a particular probability distribution function or PDF to a given data set. So, we will look at these 2 different methods with some examples, but I would like to stop at this point of time, and we will come back and look at it tomorrow.